Hi guys, my name is Samuel Kamau, yet with another lesson entitled Signal Flow Graphs. The first is to define what is a signal flow graph. A signal flow graph is a graphical representation of signal flow through a control system. Below there is a signal flow graph I have drawn, and with this signal flow graph, we can be able to see various terminologies that are used for signal flow graph. That is, we have the source node where our signal comes from, and then we have the arrows where it shows the direction the signal is flowing. And the signal flows, and finally it terminates at the sync node. The various terminologies used for signal flow graph are as follows. First, we have the branch, which connect two nodes. And then we have the source node, we have the mixed node transmittance, we have also the loop, even as it is shown. You can see for yourself all these terminologies illustrated by the use of the signal flow graph. The first terminology we are going to describe is the branch. The branch is the one that joins two nodes. And then we have the input node, also called the source node. That is where the signal originates. And from there we have the output or sync node. This is where the signal terminates, and it has only one incoming branch, unlike the source node, which has only an outgoing branch or branches. Then we have the mixed node. For the mixed node, all the other nodes except the source node and the sync node are called mixed node. These ones have both the incoming and outgoing branches. Then we have the transmittance. The transmittance is the gain along the branch. It is written as G1, G2, and so on. We also have the forward path and forward path gain. The forward path is that path that goes forward. As it is said, forward ever, backward never. So this forward path follows forward route and from the source node to the sync node. And then if you multiply all the gains along that path, we call that one forward path gain. Then we have the loop and the loop gain. For the loops, that is where we have a signal flowing allowed a certain route and then coming back to the same point. That one we call it a loop. That is to say, a path that originates and terminates on the same node, and with no other node transversed twice. This is what we call a loop. And the product of the gain allowed the loop is what we call loop gains. Non-touching loops. For the non-touching loops, those are loops that do not have any common node or branch. They are called the non-touching loops. As we continue, you will be able to see the non-touching loops in our examples. Properties of signal flow graph. We have several properties there, namely the signal moves in the arrow direction. And then we have the gain of the signal flow graph, which is calculated by Mason gain formula, even as we shall see later. And so on. Those are the signal flow graph properties. We compare the signal flow graph and block diagram. One, the self loop does not exist in block diagram, but it exists in signal flow graph. Then when we want to determine the signal flow graph transfer function, it is easier compared with the block diagram. Because in the block diagram, we have to perform block reduction method, technique, which is a bit more rigorous. So signal flow graph are easier to use to find the transfer function. Both of the systems use Laplace transform integral. And then the summing point and takeoff points are separate in block diagram, but in the signal flow graph, we can put them together. Sometimes they are together, sometimes they are separate. Construction of signal flow graph from block diagram. All variable summing points and takeoff points are represented by the node. And then if a summing point is placed before a takeoff point in the direction of signal flow, we can represent that the summing point and the takeoff point as a single node because we are not changing the output. You find that whether you combine them or they are separate, the output from the node will still be the same, and so they can be combined. But in case where we have the takeoff point placed after, that is to say, if the summing point is placed after the takeoff point, in this case they are represented by the separate node. This is because there is a change in the output from the takeoff point, and we do not want any change as a result of movement. Just in block diagrams, when we move blocks and takeoff points, we normally are supposed to have the same results of the output. Then we label the branches. Along the branches, we put the arrows. The arrows are put along the branches. Let me go back there. Label branches with corresponding transfer function. So near the arrow, we put the transfer function. And then we also are supposed to negate. If the summing point had in the block diagram had a negative, then we transfer that negative to the transfer function of that branch. Then Mason gain formula. So when we deal with complex control system having interconnected components, feedback loops and multiple paths, we use Mason gain formula, even as it is illustrated below, where n is the number of forward paths, then we have the pk gain of the kth path, and the delta. The delta is equals to 1 minus summation of all the loop gains. So you check all the loop gains, then plus non-touching loop gains taken 2 at a time, and then minus non-touching loop gains taken 3 at a time. Meaning that if you are taking 2 at a time, you multiply the gains of the 2. Then you look for another 2, you do the same. Then from there, we come to the delta k. Delta k is equals to the delta when it is calculated with the kth path removed. We shall see later how we do that. There is an example there. For the example, we are supposed to find the transfer function. The first thing we write is the loop gains. We note the loop gains. The loop gains are actually supposed to be 4 according to us. We have L1, L2, L3, and L4. So we write all the loop gains even as shown below the loop gains heading. Then you have the forward path gain. This one has 2 forward path gains. The first one is you follow the straight line from RS, that is the input, to the output, which is CS, which is in terms of transfer function is G1, G2, G3, G4, G5. Then there is also a second path where we follow the root of G6 and G5. So those are the 2 paths. Using that, we now come and use the Mason gain formula. In this case, we have 2 paths. So when we use the 2 paths, it will be P1 delta 1 plus P2 delta 2 all over the delta. So we find that the P1, which is the path number 1, we write the gains for that. And then the delta 1, the delta 1 is equals to 1 minus 0, because when we remove the first path, going back to the diagram, if we were to remove the first path, which is the straight path, it means there will be no loop left. All the loops will be terminated, and that's why we write 1 minus 0. If we go to the delta 2 for the path number 2, if we remove the second path, we find there is 2 loops that are going to remain, that is L1 and L2, so they must be included after writing the path gain for P2, which is G6, G5 into bracket 1 plus G3 plus G2, H1. These are the loops that remained after you removed the second path. And finally, using the Mason gain formula, that's you are going to get the transfer function as stated below. Then we come to another example, example 2. You're supposed to get the transfer function for this signal flow graph. First of all, the forward path gain, we only have one path, and this is the straight path going through the branches G1, G2, G3. We don't have another path, but we also have 3 loops. The 3 loops are namely they have their gains. I have stated the gains there. As you can see, L1, L2, and L3. Those are the gains, and all of them have a negative transfer function. Using the transfer function now finding the transfer function, we come again and see for the P1, we have G1, G2, G3, and the delta 1 minus 0. 0 comes because if we remove this, the forward path gains, then we will be left with no loops, and so we put 1 minus 0. Finally, our answer is going to be given as shown. That is CS over RS. We get the transfer function as shown. And so, guys, we come to the end of our lesson today. Coming up next, system modeling. Please subscribe. Bye bye. Thank you.